Only 50%, I think. Okay, we will start the lectures. Today is 31st, the last date of this August, 31st date 2020. I think you all forgot which unit you have started. I think you have started which unit? You remember? Which unit we have started? See, this is the response from you. You don't know which unit you have started, where we left everything. Okay, you have started the unit number 3, that is satellite link design. Okay, let's take a quick review of this. In that, the first point is basic transmission theory. You have seen the sum of the derivation in that. This is derivation is very important. In this, they have seen the sum of the equations. The equations are nothing but the total power received is equals to PTGT divided by 4 pi d square. And next is with respect to aperture antenna with receiver and aperture antenna with respect to the gain, transmitter gain and the receiver gain. You have seen the two equations in this. The transmission gain is 4 pi AT divided by lambda square, and the receiver gain is, that is a GT is equals to 4 pi AR divided by lambda square. With respect to this, based on this, we have seen the aperture antenna, that is AR. We have calculated that AR, and the same AR will be substituted in this equation, and we will get the final equation. The final equation you have written, I think, and based on that we have seen some of the numericals, and those numericals will be converted into the decibel values, equation into the decibel and the normal value, and we have saw some of the numericals on this. This is the first point, and the second point is system noise temperature and G by T ratio. The system noise temperature in this, you have to calculate the signal to noise ratio and gain to transmission ratio. Okay, and in this we have seen the two equations, that is noise power and noise voltage and noise current. Okay, noise power is equals to what? Vn square divided by 4R. And the noise voltage, you have to remember this equation, that is square root of 480 dr. Based on this, you have to solve some of the numericals. And the noise current is equals to square root of 4 kTb divided by R. These are the two equations. And you are calculating the noise figure, and you have to calculate the noise temperature based on this. I think you saw some of the numericals, and remaining numericals is shown at the time of tutorial. And I told you previously at the time of tutorial, you have to give some of the presentation in 5 to 10 minutes. So be prepared, because of Capgemini training you are left. You have not conducted any tutorials. So be prepared in next coming days. So this is, you also some of the numericals, I think, based on this noise temperature and G by T ratio. And we have seen G by T ratio also. Here we left in the before 15 days. And next is last part of this unit is a link budget. A link budget. Which are the two links are there? Anyone? Which are the two links? Which are the two links?
Uplink, downlink.
Okay, uplink and downlink. Uplink is from which? Uplink is from
Mobile station to the satellite.
Okay, in this we are given a mobile station. Actually, you have considered this one as an example as a mobile station. Okay, actually is nothing but what? The uplink is from a station to the satellite, and the downlink is from satellite to the earth station. We have seen this the same part in the mobile communication. Okay, the same part you have considered in the mobile communication. That mobile communication is something, but you consider this one as an example for uplink design. The mobile communication, in this we are using the mobile station, that is from mobiles to the base station, and from base station to the earth station, that is to the mobile. So in this, the from mobile station to the satellite, and the signal is goes from mobile station to the satellite, and the signal is received from satellite to the earth station, that is to the reverse, that is downlink. We are seeing one of the diagram here, that is uplink design. In this uplink design, how they are going to manage the required budget particular to the uplink and to the downlink. In this uplink design and the downlink design, we are going to use some of the frequency bands. You have seen the frequency band, that is C band, Q band, and Ka band. These are the frequency bands we are going to use, and based on that, we are going to allocate the bandwidth with to these frequencies. We are going to allocate a bandwidth to the frequencies. Okay, you are seeing this diagram. In this diagram, what you are seeing, that is the mobile station, that is user equipment. The mobile station is nothing but your user equipment, that is your smartphones. Whatever the signal is coming, that is going from mobile station to the satellite, that is to the required antenna. In this, it is going to have some of the losses. The losses are nothing but different. That is, it's going to create a loss from the buildings. It is going to create a loss from the earth stations, the weather conditions. If the distance is more from earth station to the satellite, is going to cause some of the losses. And again, some of the gains are going to provided in this particular system. Okay, that signal is reached to the particular antenna, that is to the satellite. That signal is in base station, that is, that signal is baseband signal. The baseband signal is nothing but there is no without any modulation. If you require modulation, you have to change the particular frequency of that. Okay, that frequency has to be changed, and then it is given back to the earth station, that is with respect to the sensitivity. Okay, it is having some of the loss and it is having some of the gains. We'll see some of the losses and some of the gains present in a particular uplink design. Similarly for particular downlink design. Okay, what is the sensitivity of human voice? The sensitivity of human voice is from 20 hertz to 20 kilohertz. Whatever is speaking, that is the sensitivity. It is called a sensitivity of a human voice is of 20 hertz to 20 kilohertz. If your signal is less than 20 hertz or 20 kilohertz, you can't hear the voice. So you can't hear the voice. That signal must be greater than 20 hertz or that is near to 20 kilohertz. If that signal, your voice signal is less than this, you can't hear the voice. So the minimum level of the sensitivity of a voice signal is 20 hertz to 20 kilohertz. Okay. In this uplink design, you have to see some of the losses and some of the gains. What are the losses present in a particular system and what are the gains present in a particular system while you are transferring the signal from mobile station to the satellite and from earth station to the satellite. What it means? User equipment. You have to consider one example, that is user equipment, that is your mobile station. The particular mobile station has a frequency of 15. Okay, that 15 is having some of the gain. It is given to see that the uplink forward, that is uplink arrow mark, is nothing but your gain. Uplink is nothing but your gain, arrow mark, up arrow mark. The down arrow mark, that is your loss. Down arrow mark, that is your loss, and the up arrow mark, that is your gain. You have mentioned the frequency as that is 15. Okay. When it is started moving, when it started the signal, first it is goes to your antenna. That is first it is go to your antenna. Okay. That antenna is going to give a gain. That antenna is going to give a gain first. That is, you have to add, that is plus 10. You have to add whatever you can add. That is, if you want to add 5, if you want to 2, 10, whatever it is. This is the random example I'm taking. So you adding, that is 10, that is become 25, and the signal started penetrating, and once it is the antenna has reached to the earth station, it has to come to the earth station. In that, it is started losses. Which are those losses? The first is slow fading. Slow fading is nothing but, the fading is nothing but, it is because of your weather condition. Because of your weather condition, it is going to hamper your signal. The signal will get distracted. So we are using, that is what, -1. That is, first is antenna gain, that it becomes +10 +15, that is 25. The losses is, the first loss is slow fading, that is -1, that it becomes 24. And again the signals start penetrating. One more loss is interference margin. Interference margin is nothing but what? When the two signals will interfere with each other. Interference. When the two signals are interfere with each other, that is called as interference. It is going to create a disturbance in the signal. That is -2. So you have consider -2. That becomes 22. And one more loss, that is your body loss. Next is your body loss. Body loss is nothing but, is your urban area or your rural area. Body is nothing but, is your urban or your rural area. Depends on this, it is going to give some of the losses. That is -2. That becomes 20. And next, penetration loss. This penetration loss penetrating to the buildings. Number of buildings are present in urban areas. When the signal started penetrating, it is to be hampered. It is going to hit reflection, refraction, diffraction. These are some of the words coming when the signal is penetrating. It is going to reflect from the buildings. It is going to refract from the antenna. It is going to reflect from the trees. That is, some of the penetration losses comes under, that is -5. That becomes 15. And last loss is nothing but, that is your path loss. The path loss is a distance. Path is nothing but what? That is your distance. How much is the distance? That is for a long distance communication. That is a signal will little bit distracted. That is why you are considered, that is a -10. So you'll get F5. Once all the losses are over, that is reached to the particular receiver antenna. It is reached to the particular receiver antenna, and the signals start penetrating. Once it is reached to the receiver antenna, that antenna is going to give a gain. Antenna will give a gain. That is gain is of +10. That gain is of +10. That is 10 + 5 will become 15. That is gain. That is upward mark. That is up arrow mark. That is +10 + 5. That becomes 15. Once it is reached to the particular antenna of the receiver and started, goes to a station. At this earth station, there is a cable. There is a coaxial cable is present at the receiver antenna. That is, this cable is going to provide a loss. This cable is going to provide a loss. Only antenna will give the gain, and the amplifiers will give the gain, and modulators will give the gain, and encoders will give the gain, and remaining all provides the losses. Remaining all parameters will provide the losses. So last is of cable loss. So finally we'll get the answer as 14. 14. Okay. If you design your signal is above 14, If your design signal is above 14, then and then you can hear the voice. If your design the signal is below 14, you can't hear the voice. This is what the simple random example how to design a particular uplink, how to design a particular downlink. Same parameters you are considering the downlink design also. Just the diagram has been changed. That's the reverse process you are changing. That right side figure will come in the left side and the left side figure will come in the right side. That's it. That is uplink and that is remaining is downlink. Okay. In this, he has added a one more parameter. Instead of in mobile communication, they have mentioned only the uplink design example and the downlink design example. But in satellite communication, they have to perform, they have to see the how much is the noise power present in a particular system and how much is the EIRP is present in a particular system, that is effective isotropic radiated power, and how much is the carrier to noise ratio is present in a particular system. Everything they have to perform and they have to calculate. So for that, they are going to design some of the parameters. In these parameters, the main important parameter is a carrier to noise ratio. Carrier to noise ratio is nothing but what? Carrying the signal. How much is it going to carry the signal and how much is the noise is going to added in that particular signal and how much is the loss is going to provide. That is going to one of the main important part. So the overall carrier to noise ratio is equals to what? Received power minus of noise power. Received power minus of noise power. Received power is how much? And how much is the noise noise is present in particular a system with respect to the power. It is assigned in, that is decibel hertz. Which are the parameters we required in this uplink design? So first is EIRP. EIRP we have seen that is in the first derivation, basic transmission theory, effective isotropic radiated power. Effective isotropic radiated power, that is EIRP. So EIRP is equals to what? PT into GT. PT into GT, that is transmitted power into the transmitted gain. That is EIRP. And the receiver gain is GR. Receiver gain is GR. Next, you have seen a path loss, that is LP. Path loss is LP. In that, losses are started. Some of the miscellaneous losses are there. That is a transmission loss, that is a receiver loss, and the atmospheric losses. These are called as miscellaneous losses. So miscellaneous losses is LM. And the received power is assigned by PR, and Boltzmann constant, that is K. Next, system temperature, that is T of S. Next, noise bandwidth, that is B of N. And the noise power we are assigning here for two set, that is of 2, that is N or PN. Noise power will be assigned in the terms of N or in the terms of PL. So you have seen in this particular the previous basic transmission theory, that is the received power, that is P of R is equals to PT GT GR divided by 4 pi square D square into lambda square. That is the formula. But in this uplink design, the received power is equals to, write down this equation, that is PT GT GR divided by LP into LM. LP is nothing but that is a path loss, and the LM is nothing but your miscellaneous loss. Miscellaneous losses. This is the normal equation. If you want to convert this equation into the decibel equation, the decibel form, so total received power, that is PR, is equals to what I told in the previous, that is in there, that is the numerator is always positive if there is a multiplication, and the denominator, that is, becomes negative. Okay, so 10 log of PT GT. Instead of that, you can write like this also, that is 10 log PT plus 10 log GT also. Instead of that, you can write 10 log of PT GT. That will becomes what? EIRP. That becomes EIRP, effective isotopic radiated power. Plus there is a multiplication is there, so that becomes plus. So 10 log of GR. Next remaining part is divided by, that is division. So minus 10 log of LP, minus 10 log of LP, that is your path loss. Next, minus 10 log of Ln in decibel watts. Or you are seeing in the basic transmission theory or in the noise temperature, there is a one formula for calculating a noise power. That noise power is equals to KTBN or KTB. That is the formula is KTB. But in this we have modified, that is noise power is equals to KTSBN. That is TS is, that is system temperature, and the BN is noise bandwidth. If you want to convert this into decibel, you need to add any 10 log, 10 log, 10 log. Okay, these are the constant values. Okay, these are the constant. You are cancelling, that is considering the transmitted power, receiver gain, everything and all. So K plus TS plus BN. And previously you have seen, that is the overall carrier to noise ratio is equals to what? PR divided by N. Or instead of that, we can write C by N is equals to PR divided by P of N. So C by N is equals to, that is in watts. If you want to convert that into decibel value, so C by N is equals to PR minus of N. This is what the uplink design. The previous year question paper, what he has asked, based on this, he has asked one numerical. Based on this, he has asked one numerical. You have to calculate the total received power and the noise power, and considering these two, received power and the noise power, you have to calculate the carrier to noise ratio. Carrier to noise ratio. This is what a uplink design. This is what uplink design. Similarly, for downlink design is what? Downlink. Just we have reversed a diagram. Downlink is from satellite to Earth station. Downlink is from satellite to Earth station. So same method we are using in this. The satellite to Earth station is nothing but there is a cable first, and the Earth station is your mobile station. And instead of that, you are using the cable loss, tower, antenna gain, cable at the satellite. Once it is reached to your Earth station, that is your mobile station. The number of losses and number of gains are present in a particular system. That is the trees and buildings, and these are the penetration losses. And there is a path loss, that is the distance is higher, that is called as a path loss. Okay. And again we start the same example with the same spirit, that is how it is going to use a particular frequency to hear a particular voice, that is for communication purpose. So the transmitter is of 45 dB. Transmitter is of 45 dB. Okay, we consider the random example as 45 dB. Started penetrating. The signal is started penetrating. We remember, I will ask you the question in the next lecture. Start penetrating. There is a first is is of loss, because always the signal will pass through the cable. Always the signal will pass through the cable. So there is a satellite is there. There is a cable should be there. So that cable will provide a first loss. That is down arrow mark. Down arrow mark is shown, that is a loss, and the up arrow mark, that is shows a gain. Thus, first there is a cable loss. There is cable is now using filter cables. Okay, that is becomes -1. That becomes 44. Okay. Next, once it is reached to the cable, once it cross the cable, it is reached to the antenna gain. What it is going to give the gain, the other gain and the antenna gain. Antenna gain will give. You can take any random value, not a first only 10, 8, 9, 5, everything. You can take any random value. Okay, that will become 54, and other gains are present in a particular antenna. That is, other gains are amplifiers, encoders, modulators. These are the other gains. That will be +2. Once it is, all the gains are over and started losses. Signal started penetrating. The first loss is your slow fading. Slow fading margin, that is -1. And the next loss is your interference margin, that is your -5. And the next loss is your path loss, that is the distance loss. And next is your penetration loss. And next penetration, after this body loss, if it is a rural area or the urban area, depend on this, is going to provide a particular loss. And once all the losses are over and it is reached to the again at the receiver end, and this gain is going to give a gain that is a positive, not a minus. With respect to this, you reach to the particular mobile station. And mobile station, the frequency is more than that. Your received signal is more than the desired signal. Then you can hear a voice. If it is less than that, you can't hear the voice. This is what they are going to design, a particular uplink and particular downlink design. Okay. And similarly, we are seeing in the uplink design, same part you are going to use this. There is no changes, whatever you are using in the uplink design, and the same parameters you are going to use in the downlink design also. So carrier to noise ratio, that is PR divided by N. If you want to convert that into the decibel value, so C by N is equals to PR minus of N in decibel. So EIRP, PT into GT, receiver gain, that is GR, and the path loss, that is LP, and miscellaneous loss, that is LM. So if you want to use a particular received power, that is PR is equals to PT GT plus GR minus of LP minus of LM in decibel meter. And similarly for this, N noise power, Boltzmann constant, that is key, system temperature, that is TS, noise bandwidth, that is BN, and if you want to see the noise power, so K plus TS plus of BN in decibel band. So total received power, that is PR is equals to PT GT GR divided by LP into LM, and total noise power N is equals to K TS into BN. This is what the concept of a link budget, that is from uplink design and the downlink design. And you have to solve some of the numericals. Be prepared tomorrow. You have to be ready with your calculator, and we'll solve some of the numericals on this. It is very easy numerical. Just you have to put down value on this and you have to solve. I will give one today's time. Tomorrow be ready with your calculator. So we'll solve some of the numericals on this. After solving this, we'll complete this unit. So last part of this unit is satellite systems using small Earth station. Satellite system using small Earth station. Which are the satellite systems you have seen in subsystems, satellite subsystems? One is in the second unit. Satellite subsystems is your telemetry, tracking, command, and monitoring. TTC and M. Telemetry, tracking, command, and monitoring. And the next subsystem is communication subsystem. Okay, in communication subsystem, what is required? The most important point and the most important block is your transponder. Transponder function is what? I think you forgot. Transponder, anyone? What is the actual function of transponder? Transponder.
To collect the signals from Earth station and convert it and again send back to the Earth station.
Very good, Dhanur. Whatever the signal is received from the Earth station, that is of baseband signal, and that signal will be modified, changes the frequency, and send it back to the Earth station. That is a function of transponder. In this communication subsystem, we require two systems. One is transmit system, one is receive system. Transmit system is to transmit the signal, that's it. And the receive system is to receive the signal. And all the process will be done only in the transponder itself. To change the frequency and done the modification and send it back to the receiver antenna. That is, all the process will be done through transponder. That is the function of communication subsystem. What is telemetry, tracking, command, and monitoring? Telemetry tracking. What is the actual? How much is the fuel is remaining a particular satellite? You have seen the first system, that is first stage, second stage, third stage, and the final stage. That is how much is the fuel is remaining. Is that satellite is revolving around the particular orbit or not? Is it stable or not? If it is changes is stable, you have to fire the exact thruster. After firing that thruster, it is come back to the particular stable condition of that particular orbit. That is seen by telemetry and tracking. You have to track the particular satellite, where it is located, where it is heading, how much is the distance. Everything will be monitored through the Earth station. Command is nothing but whatever, if you want to do some of the operations by ordering and sitting at the Earth station, and you have to give one command to the particular satellite, that command will be execution. That execution will be done through the by sitting at the Earth station, and finally execution is done, that will be received to the Earth station itself. That is to be monitored by sitting at the Earth station. And next, power subsystem you have seen. And this power system is consist of two types. One is batteries, one is solar panels. When the solar panels are unable to give energy to the particular satellite, the batteries are activated. When the solar panels are there, the batteries will be as in normal condition. So all these types and all these subsystems you have seen in the second unit, that is satellite subsystems. So this is what in a particular Earth station, how the satellites are going to work and how the particular subsystems are going to support to the particular Earth station. This is what the last part of this unit. Okay, tomorrow by solving these two numericals, we'll complete the unit and we'll solve remaining numericals also. And we remember in the next Saturday or Friday, I'll take a test on it, number 3. Be ready for this. And I hope I have completed the unit number 3, and tomorrow we'll complete this unit by solving some of the numericals on this. Okay. So today we'll stop here, and give me your attendance.